Sungge, please try to record. Yeah, so again, good morning, good evening, depends on where you are. So welcome to the final session of the CAFAT Global 2021. So today, essentially today it is our very exciting topic about the next 50 years of CAFAT. So this is I believe this is critical for all of us, right, to figure out we have very successful last 50 years, right? But what we should do in the next 50 years, that's a very important topic to everyone. And of course, we will also have the poster session. So the students got the best poster awards will be there in the Gather Town poster room. And talk about their research.
There's echo from your voice.
You cannot hear me?
I can hear, no problem.
Yeah, okay. So, all right. So if you cannot hear me, let me know. All right, okay. So that is the overall agenda. And today, this is the agenda for today. So the first item will be, the first talk will by Ji-Cheng Zhao. And then we will have regularly 15 minutes break through Gather Town. And after that will be the last talk of the whole conference, or will be by Professor Zikui Liu about the ocean of data. And right after that, we will do a Q&A session. So for all the attendees, if you are not familiar with this, so don't use the chat box. Please click the Q&A session, right? So that box, and type your questions there. So we will read the Q&A session, right? That box, and then if we find you, and then we can promote you as the co-host, and then you can ask your question, right? After that, we will have the closing of the CAFAT Global Conference by Professor Zikui Liu. And then we will have Martin here to talk about the organization of the 2022. So she probably will show some details there. And after that, we will get into this poster session, right? So you can go to the Gather Town, you can attend the poster session, or you can just chat with your friends. So that is pretty much the arrangements for today. And after this conference is officially closed, we still have some like a poster conference session. So this is pretty much the workshop. So here, this slide shows the details there. So if you're interested, click that button, right, to register. Okay, so that is pretty much what we are planning to do. Okay, so today, let me stop sharing. We will have, so Professor Ji-Cheng Zhao to give his excellent speech. So Ji-Cheng is currently Minta Martin Professor, and also the chair of the Department of Material Science and Engineering at the University of Maryland. So he was program director of APARI, and he was also a professor at Ohio State for quite many years. Before that, Dr. Zhao was a material scientist and Global Research Center for 12 years. And told a lot of okay. So he hold a lot of patents, and also he's a winner of the Awards from GE. Dr. Zhao is a fellow of both ASM and MRS, and received the William Hume Rotary Award. Okay, so JC, you can share your screen and start your talk now. Thank you.
I see my screen.
Yes.
It's a full screen mode.
Yeah, full screen mode.
Okay.
It's fine. Yes.
Okay, thank you very much, Yu, and thank you the organizing committee for inviting me for this talk. I'm really honored to be in the same session as Sukui for talk about the next 50 years. That's a very big topic, too big for us to handle, but we'll try to give our perspective. But my main technical talk will be on how to holistically integrate experimental computational approaches and the data to rapidly establish databases for CARE-FAT. So some of those work are mostly funded by NSF, National Science Foundation, and then US Department of Energy. And then the earlier work was funded by GE. I really want to, a lot of work I'm going to present today, on the topic of diffusion. So my students, Wei Zhong, Qiaofu Zhang, and Zhuang Ji-Cheng, and three of them played the biggest role in really getting all the data and analysis done. Okay, especially Wei Zhong did a lot of work. You will see their name in the papers associated with this work. Okay. Okay. So here's the brief outline of what I'm going to talk about. I'm going to have a one chart introduction about diffusion multiples. Many of you already know what it is, but just in case some of the audience doesn't. And then I'm going to really focus on diffusion coefficient today, okay? And then for the other ones, phase diagrams and other phase-based properties and phase precipitation, I only have a couple of charts for each topic. So don't worry when the diffusion coefficient discussion is very long, and that's intentional because the other topics are short. And then at the very end, because we're talking about the next 50 years, I'm going to offer my perspective on a bit about the field and what the strength of the approach is. So let me start with the introduction. So this is the what I call the diffusion multiples. So basically, instead of making diffusion couples that this has been used for phase diagram determination and diffusion coefficient extraction for more than a century. And this is a very mature technology. People have been using. I can see that a lot of the solid state phase diagram, these tie lines are from this local equilibrium at the interface. You can see the composition jump from here to here. That's how those pairs of tie lines are determined. Right? So this is have been used for many years. There's nothing new in there. Okay, but there's one thing that I thought this is around a little more than 20 years ago. So if we can take advantage of the composition gradients and have localized property measurements, then we can establish composition dependent properties without making individual alloys. That requires high spatial resolution measurement technologies. So I spent a lot of time develop those technologies. I'm going to talk about that later. But at the beginning, I'm going to focus on phase diagrams and diffusion coefficients that can be extracted out from the diffusion profiles. So there's a binary diffusion couple. So this has been in existence for many years before me. And then I learned how to make diffusion triples from my former advisor, Professor Jin. And so this is how basically put the three pieces together so that we can take advantage of the diffusion among three of them. I even made a diffusion triple as part of my master's degrees dissertation at that time. In the US, John Propeshko and Dan Thoma, did one triple in 1990, published in 1994. So when I was at GE, because it's very time consuming to make triples one at a time. So I developed this method to combine many diffusion triples and diffusion couples into a single sample. I call it diffusion multiple. So in this sample, this is a piece of nickel, an inch and a half diameter nickel. We cut a slice out from that, a chunk out of that, and then using wire EDM to hollow out the inside and basically polish it to make it clean. And then we put a different piece of metals like chromium and iron, nickel, and molybdenum inside. And then we put a cap on the top and the bottom. And then we send out to a company to do electron beam welding, basically welding the cap inside. So that's in a vacuum state, inside the vacuum chamber. So the inside is vacuum, and then we use a hot static press. So basically put this one in an argon environment and squeeze everything together at high temperature and pressure. And then we take it out and we do a heat treatment, long-term heat treatment to promote all the diffusion and so that we can measure diffusion coefficient, we can measure phase diagrams. So each corner can, this triple can allow us to measure the entire Turner phase diagram. So this is the example for iron, chrome, molybdenum. Okay, so the very efficient way of getting tie line information, like what Greg was saying. Greg Rosen was saying the other day about the importance of that as one of the genes of materials. So that's the phase diagram determination part. Okay, so it's but the property of measurement, because we can create all the single phase compositions, just like in this case. In the binary case, we can get the all the single phase composition. The ternary, we can get all the single phase composition as well. So if we have a way to measure properties, then that's very efficient. So that's I'm going to talk about that later. Okay, so that's the basically approach that I've been taking for a long time. So let me talk about diffusion coefficients. It's a topic, as you all know, atomic mobility is extremely important for the simulation of many different materials, phenomena, and properties, and so on and so forth. So there are various phenomenological diffusion coefficient, right? So this is the self-diffusion coefficient. If you do tracer experiment, you can measure the iron in iron tracer, and then you can put a small amount of nickel tracer on pure iron and get the tracer data for nickel in iron. That's usually what is done. On this side, you got iron in nickel and nickel in nickel. So those are the boundary conditions. So this is, we can call this lattice mobility, what the Young Morgan talk about. So if you have an alloy and you do the same thing, let's say you have an alloy, you put a nickel tracer, and then you get a diffusion coefficient of tracer, and this is the iron tracer diffusion coefficient, right? So if you plot the tracer as a function of composition, that's the dashed line, and then the red circles are when you make a diffusion couple, and then you measure using the Boltzmann-Montano analysis, you got this diffusion coefficient as a function of composition as well. So those are two fundamentally different kinds of diffusion coefficient, but they're related by the Dawkins equation, right? You got tracer data, this is and then you time the thermodynamic factor, right? That's basically said, are you accelerating or you're decelerating the diffusion? So when the atoms like each other, like in the ordered phase, you start to order the state, delta H equals negative, you got the acceleration. When the delta H is positive, you decelerate, right? The atom does not like each other. So it's this Dawkins equation is a beautiful separation of the kinetic part and the thermodynamic part. So in order to do a good assessment of a binary system, you need those data for the pure elements, the self-diffusion coefficient and impurity diffusion coefficient, or dilute diffusion coefficient. one can clearly see that when you talk about the interdiffusion coefficient, it touches both sides as the impurity, not the self-diffusion coefficient. So this is an important point, right? So it's the impurity diffusion that is dictating where this curve is going to land on both sides. Okay. So over the years, we you know, the worldwide effort have collected quite a lot of dilute or impurity diffusion data using the tracer experiment. But those work were focused, this is how many measurements, sets of data as a function of years. You can see that's very much focused on, concentrated on the 1970s and 60s and 80s. And now there's very few measurement using tracer because there are very few funding agency would fund those ones. So, but we still need, if you look at the metals, just look at the metal, we still need 4,000 impurity diffusion coefficient sets. Okay, these still have not been measured because impurity, you need a lot of data, right? For each element, you know, like niobium, we need all the other elements impurity in this particular element. So this, you need a lot more data than self-diffusion coefficient. We only have about 61 or 65 metals in the periodic table. So that's only that many in self-diffusion. So, you know, over the years, we developed this method called a forward simulation analysis that instead of doing the Boltzmann-Montana analysis, we basically assume a function and then we use the Dawkins, use the diffusion equation to simulate until the match. In this way, we can get a very accurate impurity diffusion coefficient just from the simple diffusion profile of that we got from diffusion couples. So we have tested this method over a very wide range, a large of more than 130 some elements in there. So this is a very efficient way of getting impurity diffusion coefficient. As I mentioned, it's very important for establishing diffusion database. So this is mostly established by Qiaofu Zhang when he was with me. He's now at the Questec. So we have this program called the Pi diffusion program that you can download from GitHub. Quite a lot of group will have done that. And we also write a short article to describe how to use it. So if you're interested in using the tool, you can do that. So use those kind of tools and using diffusion multiples, we were able to collect a lot of data, right? So this is a titanium diffusion multiple that I made, and this is another one we collaborated with Professor Liang Jiang. So two samples, we collect more diffusion data of BCC titanium than the whole world combined almost, in terms of how much data we collected. And for us, this data, as you extrapolate in this one, this agree with the independently measured impurity really well, right? So some of the data set, if you extrapolate, in this case, you can see if you extrapolate that data to the impurity, there will be disagreement with the one. So we have very good confidence because those are literature data impurity. This is our data. Without we did not input the tracer, the impurity data in our modeling process. So this is an independent check of how reliable the data set are. Okay. And then, funded by Department of Energy, we were asked to develop a mobility database, a diffusion database for magnesium alloys. So we come up with this a very innovative way of making samples really fast. This is a piece of magnesium. We drill into it halfway through, and then we put a piece of other metal like aluminum or a master alloy, and then we put a piece of magnesium on top, and then we put a piece of pure iron, and then we use a screw to tighten it up. This is all made inside a glove box, a pure argon glove box. And then we can take it out because there's so much contact here that when we take it out and seal off in a quartz tube, during that process, the oxygen cannot get in. And then we heat it up, melt it, and they form a eutectic pure liquid diffuse against the solid solution. So this is big enough that they were not the liquid will just be contained in the middle. And we got a diffusion, if you do the measurement, you got a diffusion, this diffusion gradient in the solid solution. So we can measure the solubility limit very, very accurately. And then we use the forward simulation analysis, we were able to get the impurity and the interdiffusion coefficient. So we tested this one in the magnesium zinc diffusion in magnesium. You can see some of those data were tracer data, and the red dots are our measurement. You can see how accurate that is. So this allows us to make a measurement for calcium in magnesium. There's no isotope that can do the job. And if you want to do it, this is very high, calcium is very hygroscopic, right? It's hard to, and then the solubility is so low that it's very hard to make an alloy to diffuse against it. So we put an intermediate amorphous alloy and let the liquid diffuse against the solid. You can see this diffuse, the mobility, the solubility is 0.8% atomic percent, very low in arsenal. So we were able to get for the first time, calcium diffusion in magnesium in the world because there's no data. And then we can compare with the first principle calculations for, you can see that the activation energy is quite good. That's the slope. But the d sub 0, that's how far away this curve against the measurements. It has more variations. We went ahead under the DOE program to, measure the 10 different elements in magnesium. Again, we got more measurements than the rest of the world combined. In terms of the tracer and the impurity and the interdiffusion coefficient, the amount of data. From there, we established a very reliable and a very comprehensive database. Have 23 elements, okay, and this includes literature data. And then we also have 10 different elements that we provided the computed data from groups like Sequoia's group and Dame Morgan and Dallas Tranquil's group. So you can see that if we plot all the data, experimental data versus the computed data, and this is the perfect agreement in the one. So when the lines are parallel, that means the activation energy is exactly the same. When they are further away, that's the D0 is far away, further away. So you can see that the D sub 0 has some variation, but the activation energy is quite accurate. So what we have done in that case is I call it holistic integration. So experimentally using the liquid solid diffusion couple, we can get high temperature data very fast. The diffusion is only a few hours, and then we can get the reliable data. You can see because the temperature range is so small, you can't get activation energies. For example, if this data below square data, if you use the activation energy, it will be far away from the computed data. So because we did a lot of comparison, we trust the computed activation energy, and then we use the experimental data to fit the D sub 0. And that's how we can get more reliable data in that way. Holistically integrated both the experimental and the measurement to get the best out from it. We also computed, this is work with Professor Wolfgang Wendel and Miriam Zayati at Ohio State when I was there to work with them to compute the metastable phase like HCP aluminum and its self-diffusion coefficient and impurity of magnesium in HCP aluminum. There's no way to measure it, right? Because we can compute this data that's much more reliable than using such a small amount of data to fit the entire binary diffusion coefficient. So this is something I'm going to talk about more as I move along. So this is again, try to leverage both good part of the simulation experiment to do the best job. Okay. So that's the establishment of the magnesium diffusion database. So recently we performed a very detailed analysis of how many fitting parameters do we need in a Banner diffusion solid solution, right? As I mentioned, so in this case, we need to have this, mobility stability, right? Basically, it's the pure elements data on both sides, and then, how do we fit this interdiffusion and the intrinsic diffusion coefficient? We developed a model that were only one parameter, one fitting parameter, one fitting constant to be able to describe the behavior of banners. I think this will simplify a lot of things for the future. So let me just first to emphasize the fact that we really need what the Jung algorithm called lattice stability, right? So that the impurity diffusion and self-diffusion data of each element in the other. So this is a set of data, two sets of data for cobalt and iron, okay? As you can see, there's this, those are all the impurity diffusion coefficients that are very, very established before. But if you look at the data for this interdiffusion coefficient in this one, okay, on this side does not agree with the impurity diffusion coefficient. On this side does not agree this. So if you're forcefully to fit those data, you're going to get a lot, you use a lot of parameters, and it was not going to give you anything good, right? Because if this did not agree, that's not good data to use, okay? And then, if you have very reliable data for in this case, we get a very nice data of titanium in tantalum, the impure diffusion coefficient at this temperature is here. Instead, the experimental data is extrapolating into a much, much higher value, orders of magnitude high. And this is not very reliable. When this could bend over, you can see that kind of phenomenon. And in that case, you need to kick out those data. Otherwise, you're going to get very wrong results in this case, because these agree with it has to agree on both sides with the impurity diffusion coefficient, as I mentioned. So let's see how important that is to have, the foundation of the silver and the impurity. Again, you can see this set of data, bended over, and the impurity diffusion is much, much smaller. There's a very clear explanation why this kind of phenomenon takes place. Okay, and also we need the metastable states so that we can do a much better job in fitting this one. So it's extremely important, just like the lattice stability for thermodynamics. The lattice mobility is also equally important. So this is an example of the iron palladium. Okay, so you can see that this is the interdiffusion coefficient at 4 different temperatures. This is the thermodynamic factor. As I mentioned, when you have ordered phase, delta H on this side is negative. This side you have a small miscibility gap, so that the delta H mix is positive. So you can see that if the elements does not like each other, in this case, it decelerates the diffusion. This side, they like each other, you have an attraction to accelerate the diffusion. That's what the beauty of the the Dawkins equation is, right? So you can see that the impurity diffusion coefficient, behave very regular. There's no up and down. It's easy to fit with a parabolic constant. But the impurity and the interdiffusion coefficient and the intrinsic diffusion can also have a thermodynamic factor in it. So that's how the up and downs in the curve comes from. Okay. So this is basically, we found about 18 Banner system for the test. We want to go see how many parameters we really need to model the system, right? So you can see we have the systems that have very asymmetrical behavior, like those ones, right? And then we have very symmetrical behavior. We have both positive and negative. So it's a very diverse set of data. We have a lot of good data in those 18 systems. And so that allow us to do a very comprehensive test. Some of the system, the diffusion coefficient were 8 or 9 magnitude order of magnitude differences. Again, a very diverse system. So what we have done, basically, we started with, that's what the Anderson algorithm treatment, right? You start with the Einstein's definition of mobility. So this is the tracer diffusion coefficient. You substitute that into there. As you all know, in the mobility treatment, this whole term get yanked into this phi I, this mobility atomic mobility parameter. And then so this is the definition of that one. And if you rearrange it, it's become RT logarithm of the intrinsic diffusion coefficient. Somehow this simple equation was not widely used. I found it extremely useful, okay, to help me understand what's going on. So this is if you have a binary diffusion system, that's AB, that's how it writes out. If R equals 0, then you got a single parameter. This one, usually people use A plus BT for each element. So you got 4 parameters, 4 constants to fit, right? So that's what we went ahead, we tested all those different combinations. We tested the 4 parameters. We take out the temperature dependent one, 2 parameters, and then we have this 2 equal, so 1 parameter. That's what we did in this case. What we found is that you can simplify the binary diffusion and still have extremely good description of the system behavior by taking out all the temperature dependent terms. You never need that. Okay, we tested in 18 systems. Some of this one as the data covers from 800 degrees to 2000 degrees, 1200 degrees C temperature span. Most of the system you don't have that wide temperature. Even for those systems, none of the system requires this one. So that's the basic message. Now, if you really want to use 2 parameters, go ahead. But what we found is that this 2 parameter can be equal and still do a great job. Okay. So if you use that, then the diffusion coefficient the equation become really, really simple. So this is the self-diffusion coefficient of A in A and A in B, that's the impurity, and B, this is the self-diffusion of B, that's the impurity of B. Every system of this one. Okay, so the entire tracer data can be described from 1 parameter, and the interdiffusion coefficient can be computed after you get that. So that's how effective. So basically, we can describe the behavior of the entire binary system of a solid solution by a single parameter, in comparison with some of the literature mobility assessment. They use up to 8 parameters for binary system. Okay, so a lot of them using 6 in the 18 system. Half of them using 6 up to 6 parameters. Okay, and you really don't need that many parameters. And this is a snapshot of some of the systems. In this case, what we did was we used the interdiffusion coefficient data to fit the single parameter. And then we use that equation to predict what the intrinsic and the impurity diffusion, the tracer diffusion and the intrinsic diffusion coefficient to be some order of magnitude. As I mentioned, this covers very different diverse systems. All of them works, okay? And again, if you look at the thermodynamic parameters, you can see as a factor, you can see how much. The other way, important thing to point out is that thermodynamic factor is temperature dependent, right? So all the binary system, because the Arrhenius equation have the temperature dependence for all the impurity and the self-diffusion coefficient, and the thermodynamic factor have a temperature dependency. The entire binary system's temperature dependency is already fully described by those dependency. There's no need to add another parameter into it. Okay, that's what we found in this. So, sorry. So this is what we found. Basically, that this B top time T term is completely unnecessary. Okay. And we found that you can use a single parameter to describe each binary system. Okay, and if you insist on using 2 separate ones, I'm not going to cry over it, but please take out the B sub T term. So not using more than 2 parameters per binary system. So this is part of the beauty of the CAFET approach, right? You can describe the entire diffusion behavior of a binary system from a single parameter, a single constant. And that's how efficient when the model is established, that you can store the data and retrieve the data and get the data. That's how beautiful it is. Okay, so basically, I usually use the logarithm DI because that helps me to understand what are the quantities. But you know, if you times RT, you get this regular mobility parameters. Okay. So we got the binary, or you know, test down. I think that's quite useful information. And then recently we have, this is unpublished work yet, and so we are presenting this ahead of publication. So this is the regular equation, right? Looks very formidable and lots of things. But if you use this simple equation converted into a diffusion coefficient equation, basically, and then it's become more straightforward to understand. Okay, so this is the tracer of A in the alloy, in any alloy. Okay, and this is the self-diffusion coefficient A. This A in impurity diffusion in B, and then A in C. Okay, this is the linear addition, and then this is the binary parameter we talked about for the AB system, for the AC system. And then for the BC system, because we are talking about the A diffusion in BC. So this is the cross binary term. Okay, this is not in the binary system. And then you got 3 ternary interaction parameters, okay, for the A. The same thing, you get B and C. So basically you can see there are 3 cross binary terms, and then there are 9 ternary terms. You get 12 terms to fit, right? So that's a lot of parameter, and usually in a lot of the binary ternary system, we have very few data points to fit. So this is, you know, if we fit 12 parameter, that's just way overfitting, right? So what we did was we went ahead and tested out various different combinations. Okay, the first thing we said, okay, we got this cross binary term, 3 parameters. We got the 9 ternary parameters, as I mentioned in the previous chart. So the first one is take all of them to 0. That's the model 0. Just extrapolate from pure binary without any interaction parameters for the ternary. And that's what the data look like. Okay, so if you do a good job in binary, actually it's not too bad. If you compare with the previous literature assessment, actually it's better than one of the parameter, one of the assessment, and slightly worse than the other, but not that much worse. And then this model 1 is we have all the 3 cross binary to be equal. We just introduce 1 ternary related parameter. You can see it gets better, substantially better than this. Okay, so this is the 3 systems. So we have cobalt iron nickel and cobalt iron copper iron nickel and then niobium titanium related. You can see introduce 1 parameter, the error of the disagreement is much less. Okay, this is a very effective way of making the model better. And the second model is model 2 is setting all those 9 parameters equal to a single constant and set all those 1 to 0. Again, introduce a single parameter, and that's not as effective and depends on the system, not as consistent. So introducing cross binary is more effective than introducing ternary if you introduce a single parameter. And then we start to add 2 parameters, this one as a single parameter, this one as a single parameter. That's a 2 parameter model, and that has a slight improvement sometimes, sometimes a little bit improvement. And then the very effective way of doing modeling is to set this one as 3 independent parameters, set all this one equal to 0. That's the model number 4. Okay, you can see now the error is much less. When you start adding more and more parameters, doesn't give us anything, right? So if 12 parameters, compared to 4 parameters, it's a very little improvement. So our suggestion is not to do more than 4 parameters. Okay, this is the 3 parameter model. That's the M4. That's the three independent cross-binary term, and that's how the system works pretty well in that case. So now, if you only do that, then the ternary interdiffusion coefficient becomes really simple. Okay, this is carried over from the binary, right? Three binary system: A, B, A, B are equal, as I mentioned. A, C, this is equal. B, C, this is equal, right? And three parameters, and then three cross-binary parameters. And then if you really want to do some, more, you have more than enough data, you really want to add another parameter, you set all the 9 parameters to a constant. Okay, that's model number 7. Okay, and you really don't need more than that. If you add another, 6 more parameters, not good, gain much out from this one. And some of the people does introduce that many parameters. Okay. So if we just using this simple model, okay, if you have very little data, then you just use the model M1, just introduce this one as a constant. I think this is a very robust and model. I can easily extrapolate using the Anderson Ogren treatment for the mobility to multi-component systems. Okay, so we believe this is going to be really useful, and very few systematic study like this has been carried out before. So the other day, Axel Manuel was saying that for thermodynamic properties, the computation and the experimental folks are almost finger touching in this case. Okay, I argue that for the diffusion coefficient, we are almost in a high 5 state. Okay, the experiment and the modeling, the agreement is become very impressive, and we can actually take advantage of both of them, and that's what I call a holistic integration. But what we really need in the future is to using DFT and the machine learning tools to really compute all the different combinations of impurity diffusion coefficient. Okay, every element on the every other element in all the 3 states, basic solutions. Again, you need HCP aluminum, BCC aluminum, right? Every other elements in the product table on BCC aluminum and HCP aluminum, and that would be what the Ogren called lattice mobilities, and that's extremely important, right? Because as I mentioned in the past, if you have very little data, because that's the solubility is only this much of that's the only thing you can measure, and you are trying to fit so many parameters, and this is unknown on the aluminum side, and use a very small data set to fit a large number of parameters. It's not going to give us a very reliable mobility data. I think that's the holistic integration of computed and experimental data really will be able to. I think the community is ready to establish this lattice stability. Right? So I think this is the really important stepstone in our quest to get all encompassing database, reliable database for all the solutions. I think our.
Tuesday, this is a reminder. You have spent 40 minutes, maybe another 5 minutes. You can wrap up.
Yeah. Okay.
Thank you.
That's about right. So as I mentioned, this is the I'm going to focus on this the diffusion. On the experimental side, with the methodologies we developed are very effective, but we do need to develop. We still need to develop a methodology to more efficiently measure ternary diffusion coefficient. I have an NSF program right now to do that. We also need to develop a methodology to measure, use long tracer method to measure diffusion coefficient down to very low diffusion coefficient. Right now, there's not a good method to do that. Phase diagram, I already talked about this many times, and I'm gonna basically say, we can, build many triples and get, many diffusion, many phase diagrams into one sample very efficiently. We have done multiple ones, like this is in collaboration with Liang Zhang, measure the cobalt-based superalloy related systems. You can see, from one sample, we got the large number of Turner systems. Okay, so in the future, I think the work we will be doing, is to measure, experimentally, it's very easy to measure high temperature ones, right? The low temperature diffusion coefficient is so slow, it's very hard to measure. The calculation side, is much more reliable. So this is at a low temperature. So we have this vertical integration would be the most efficient way of doing that. In the middle, the metastability will be the one. There are a lot of great work that on the computational side. I'm not a computational person, but I appreciate a lot of the great work that have been done. And I think to establish the fourth generation elastic stability set of strong foundation is very important. Zikui, we have a joint program. He's working on the sublattice stability using DFT and the machine learning. That's very exciting work. Okay. Other properties, so we developed tools to be able to measure locally the properties in a micron spatial resolution. So we can very quickly establish property databases from such measurement and be able to compare with the individual measurement. You can see in this case, the red dots are individual measurement. We can map it out in internal systems. So we have developed tools for thermal conductivity, heat capacity, expansion coefficient, and elastic constants. And all of them can be measured in the same polished sample across the same composition gradient. So this is extremely, effective tools to do this. Okay. So recently we developed the tools to using dual and near diffusion multiples. I really encourage you to read this paper. There's a lot of good information about how to leverage this one to collect a tremendous amount of data about precipitation. And by doing what the CARIFAT is doing, right, the match model with experiment, we can get tremendous amount of information out of those ones. So my perspective on the one, I think in the past we're doing experiment, we do analysis, we do data. Nowadays, a lot of the work we are doing is doing modeling experiment together. And that's how, just like what CARIFAT is doing, extrapolate the most valuable data from there, right? So I think, but no matter what we do, the computational will be much faster than the experiment. So we need to do the holistic integration and the use in autonomous experiment and to catch up with this gap, okay? So because we are talking about 50 years of CARIFAT, so I'm both a user, mostly like a user of CARIFAT. I did a few assessment on the thermodynamic side, and we did quite a lot of assessment on the mobility side. So I think the accuracy that the CARIFAT achieved is what the greatest strength we have, right? But we really need to establish a reliable foundation so that we this inverse parameters problem that many people are talking about to solve that. I think we are ready and we can establish a lattice mobility, just like the lattice stability, like what Young Ogren was talking about. I think this is a very exciting development. We can do that. And then the second point is prevalence. So the thermodynamics is the most prevalent science, right? So many fields use the same science, and so many different parameters can be what Zikui has shown, and he's probably going to talk about it. All the different properties, phase-based properties and beyond. And they also included the entropy production term to be able to describe the non-equilibrium phenomenon, and Zikui is going to talk about a lot of those different entropy contributions. So this basically can cover all the properties, right? This is, we did a few of those ones now, mobility and molar volume, all that stuff. But the science itself is much more broad. That's what the CARIFAT capability is, right? I think the field also have a programmatic, a very practical view, and everything we fit with Kister And it's a strength, right? I think that's very, very good. And the other point very important in my mind is what I appreciate mostly is how efficient, right? We can use a single prime to describe and store all the data for a diffusion for a binary system. And you can have a new prime to describe the entire thermodynamic descriptions of binary and ternary systems. So, because we can cover so many properties and performances, this is the most efficient way of aggregating all the materials data and knowledge into our framework, the CAFAT framework. And we are the condenser. Okay, we basically condense all the knowledge and data into a model-based science, and that's extremely I think the other thing that the CAFAT team had done is the teamwork, right? They started from Lara Kaufman, working with the DFT folks and experimental folks, and the teamwork is extremely important. And then the industry centric attitude and the test and learn attitude is let's try it out and see what we can do. That's extremely important. And the last one is expansiveness, right? There's just so much we can do in the field. I'm just using a few example of this. In the ceramic system, you can have orders of magnitude. This is plotting in logarithm scale of behavior because there's the covariant diagram, the different defects, and this can all be incorporated into the CAFAT framework. So there is an endless frontier for us in the field. So if I put all this essence of CAFAT together, right? We got accuracy, provenance, and all those efficiency and so on and so forth. We really have the appetite, right? We have strong appetite in the past, and I hope the younger generation keep the appetite, as that's what give us the strength. I think Greg talked about the CAFAT is for the calculation of phase dynamics. I would suggest that we might simplify into calculation of phase data, right? Because now not just diagrams, phase diagrams, but all the data in the field, in materials. If we are reminiscent of the CAFAT, the previous CAFAT, maybe we can say the phase diagram and the data have 2Ds, but in the CAFAT. And in my mind, CAFAT is the genes of MGI. Right? I think in the next 50 years, there's just so much exciting things that we can do to the field. So that's my summary slides and my perspective. Thank you very much for your time. I appreciate it.
All right, JC, yeah, thank you very much for your excellent talk. Yeah, I learned a lot. So for the audience, please hold your questions for a while. Now let's do this 15 minutes break. And after Professor Zhikui Liu gave his talk, then we can get into this Q&A session. I believe a lot of people will also ask JC questions. So now it is 8:55. So let's come back in 15 minutes. That's 9:10. We will send you a reminder 2 minutes before that. All right. Okay. So enjoy the gather time and please come back in 15 minutes. Thank you.